For thousands of years, the sharpest minds in history, from ancient Greece to the giants of 19th century science, all chased the same question. What is this stuff we call the universe made of? By the time the 20th century rolled around, they thought they'd cracked it. The atom. The final, indivisible piece of the puzzle. But what they'd really found was just the first clue in a mystery that was deeper than they could possibly imagine. They were on the edge of a breakthrough, one that wouldn't come from decades of slow debate, but in just a few stunning seconds. A fleeting, almost unbelievable observation that would shatter everything they knew and force us all to rethink reality itself. For years, the consensus was clear. An atom was a soft, fluffy ball of positive charge with tiny electrons dotted through it, kind of like blueberries in a muffin. Scientists figured that firing tiny particles at it would be like shooting bullets into a fog bank. But during one experiment, in a moment that changed everything, the impossible happened. A few of those bullets came ricocheting back. It was, as the lead scientist famously put it, as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. That jaw-dropping observation didn't just question the model, it blew it to pieces, revealing a hidden, miniature universe and rewriting the laws of physics forever. To really get the sheer shock of that moment, we have to go back to the world before it happened. It's 1909, and physics is dominated by one neat, tidy idea, the plum pudding model of the atom. It was proposed by the brilliant J.J. Thomson, the man who discovered the electron back in 1897, and it just made a lot of sense at the time. Thomson's idea was simple. An atom was a sphere of evenly spread out positive charge. Think of it like a thick fog or, well, a pudding. And scattered inside this positive goo were the tiny, negatively charged electrons he'd found, like plums in a pudding, or for a more modern take, blueberries in a muffin. The charges all balanced out, making the atom neutral. It was an elegant theory that explained everything they knew. It was accepted truth. And like so many accepted truths in science, it was about to be proven spectacularly wrong. The guy who would do it was a New Zealand-born physicist named Ernest Rutherford. A former student of Thomson's, Rutherford was a force of nature, a boisterous, brilliant experimentalist at the University of Manchester. In 1909, he wasn't trying to tear down his old mentor's work. In fact, he was doing the opposite. He set up an experiment to get more evidence for the plum pudding model, hoping to solidify its place as the final word on the atom. That experiment would become one of the most important in history. Rutherford, along with his assistants Hans Geiger and Ernest Marsden, put together a device that was both clever and, by our standards today, shockingly simple. The plan was to shoot a beam of tiny, positively charged particles at a target and just see what happened. Their bullets were alpha particles, which are basically just the core of a helium atom. Dense, fast, and positively charged. They got these particles from a radioactive element like radium, which they stuck inside a lead box with a tiny hole in it to create a focused beam. Their target was a sheet of gold foil so thin it was almost unbelievable. Gold was the perfect choice because you can hammer it down to be just a few hundred atoms thick. This was key. They needed the alpha particles to hit as few layers of atoms as possible. And finally, the detector. This was a circular screen that wrapped around the gold foil, coated in a material called zinc sulfide. When an alpha particle hits this screen, it creates a tiny flash of light, called a scintillation. The job for Geiger and Marsden was to sit in a pitch-black room, let their eyes adjust, and then painstakingly count every single tiny flash, one by one, marking where it landed. It was tedious, eye-straining work that required incredible patience. So, what were they expecting? Well, according to Thomson's plum pudding model, the positive charge in each gold atom was spread out, like a thin mist. It was too weak and diffuse to put up a fight. So, as the positively charged alpha particles zipped toward the foil, they should have sailed right on through with barely a nudge. Think of the plum pudding atom as a big, fluffy cloud. The alpha particle is a high-speed bullet. If you fire that bullet at the cloud, you'd expect it to tear straight through to the other side, right? Maybe it would wobble a tiny bit, but nothing major. Rutherford and his team fully expected to see all their little flashes clustered in a neat spot on the detector directly behind the foil. Any slight deviations would have just confirmed that the atom's positive charge was soft and spread out, just like Thomson said. For days, Geiger and Marsden sat in the dark, glued to the detector, counting flashes, and for the most part, everything went exactly as planned. Flash after flash after flash, all appearing right behind the foil. Thousands upon thousands of alpha particles passed through the gold atoms as if they were punching through empty space. The plum pudding model was looking solid, but Rutherford was a thorough scientist. He had a hunch. He turned to Marsden and suggested, "Why don't you have a look and see if any particles scatter through a large angle?" And this is where the story and the history of physics takes a sharp turn. Following Rutherford's suggestion, they started moving the detector, scanning the areas to the side of the foil. And then, it happened, a flash. But it wasn't behind the foil. It was way, way off to the side. Then another. And then, the most stunning observation of all. A flash on the part of the screen in front of the foil. An alpha particle had hit the gold foil and bounced almost straight back. It's hard to explain just how impossible this seemed. It happened only once in about every 8,000 to 20,000 particles, a single, fleeting flash of light in an experiment that ran for hours. But that one observation defied everything they thought they knew. Rutherford would later describe his shock with one of science's most famous lines, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." The bullet hadn't just been nudged by the cloud, it had hit something and ricocheted. The plum pudding model had absolutely no explanation for this. For a heavy, fast-moving alpha particle to be thrown backward, it must have run into an electrostatic force of enormous strength. It must have hit something incredibly small, incredibly dense, and packed with positive charge. The pudding wasn't a soft mist at all. There was something hard hidden inside. It took Rutherford nearly 2 years to really work through the mind-bending implications of those backward scattering particles. He crunched the numbers, trying to figure out what kind of atom could produce such a crazy result. The answer he arrived at in 1911 was revolutionary. He reasoned that since the vast majority of alpha particles pass straight through, the atom must be mostly empty space. This was a direct contradiction of the idea of a solid, pudding-like atom. But to explain those rare, violent ricochets, he concluded that all of an atom's positive charge and almost all of its mass had to be concentrated in a ridiculously tiny, dense center. The few alpha particles that bounced back were the unlucky ones that scored a near-direct hit on this central core. Rutherford called this dense center the nucleus. With that, a new picture of the atom was born, the nuclear model. An atom wasn't a blueberry muffin anymore. It was a miniature solar system. At its heart was a tiny, dense, positively charged nucleus holding nearly all the mass. And orbiting this nucleus, a huge distance away, were the light, negatively charged electrons. The scale is just staggering. If an atom were the size of a football stadium, the nucleus would be the size of a single marble sitting on the 50-yard line. The rest? Just empty space. The discovery of the nucleus changed everything. It completely threw out the plum pudding model and laid the groundwork for all of modern physics. Of course, Rutherford's own model wasn't perfect. Classical physics said his orbiting electrons should quickly lose energy and spiral into the nucleus, which obviously doesn't happen. It would take another brilliant mind, Niels Bohr, who joined Rutherford's lab in 1912, to apply the weird, new ideas of quantum mechanics to solve that problem, proposing that electrons exist in stable, specific energy levels. But that's a story for another time. Every major leap forward in physics for the next century, the discovery of the neutron, our understanding of nuclear reactions harnessing nuclear power, the development of quantum mechanics, it all stands on the shoulders of that gold foil experiment. It all traces back to a darkened room in Manchester, to the incredible patience of Geiger and Marsden, and to the moment a few stray flashes of light revealed a secret hiding in plain sight for all of human history. This story shows you how science really works. It's not always a slow, steady march to the truth. Sometimes it's a sudden, violent leap forward, kicked off by a single observation that just doesn't fit. A result so strange it forces you to throw out the rule book and start over. All because a few tiny particles in a few fleeting moments refused to do what they were told. If you enjoyed this trip into the heart of the atom, do us a favor and hit that like button and subscribe for more stories from the wild history of science. What other scientific discoveries do you know of that were born from a single shocking moment? Let us know in the comments below. Thanks for watching.